Hey everybody, in this video we are talking about how scientists will summarize an experiment or what they learn in something known as a CER. We're going to learn what that is. We'll see an example at the very end, maybe some resources that might be helpful. All right, that's what we're getting into. So to get started, our scientific argument, what we mean by that is how does a scientist, after they collect their data, after they do their experiment, after they form their model, how do they summarize what it is that they have learned? What conclusions are they able to make? And presenting information in science often consists of the following three things. The first item is a claim, and to be honest, in my opinion, the claim is the easiest piece. It's usually like a sentence. It's what you think is going on. What do you think the answer to the question is? What is your big overall result? If we pretend we were in a courtroom, it might be something like Timmy robbed the bank. That's the claim the prosecutor is making. Or maybe the defense attorney is making the claim of, no, Timmy did not rob the bank. It's kind of like the big idea, the big conclusion, all right? The next item is also not too tough. It tends to be what forms most in terms of how much writing you're doing, the biggest piece of the CER, and that's the evidence. It's the information or the data that supports your claim. Now, what do I mean by evidence or data? First, think of your senses. If you see something, that's evidence. If you hear something or if you touch something, but in a context of a physics class, it is often the measurements that we are making. We are often, if you're in my own physics class, going to be measuring things like distances and times, maybe temperatures, maybe forces. Those measurements, that is usually your bare bones evidence that you use to then draw conclusions from, okay? Likewise, if we were pretending we were in a courtroom, it might be the physical evidence, fingerprints, license plates, things like that. Now, the last piece is the reasoning, and I don't think reasoning by itself is necessarily difficult, but it is the piece that I feel that students, my students at least in the beginning, often overlook is maybe the best word. It's not that they don't know how to do it, but they think it's not necessary. But reasoning is how you tie these two things together. Just because the prosecutor says there are fingerprints, and just because the prosecutor says there is a camera that took a picture of a license plate, why is that evidence, or why does that support the claim, I should say, that Timmy robbed the bank? It's going into how these two things are connected. Well, the fingerprints match Timmy's, so that helps show that Timmy must have been there and they're the person who opened the vault. Or the license plate came back to this person and they were in the parking lot, so it makes sense that the person whose license plate we took a picture of was there and committed the crime. Again, in the context of physics, how does that evidence that we gathered, whatever maybe those data points are, how is it that it supports whatever claim it is that we're trying to make? And I'll show you an example at the end of this. These three things make our scientific argument what we call simply CER, for hopefully reasons that are obvious. The claim, evidence, and reasoning, CER, that's how we conclude. Usually in my own class, like a paragraph, sometimes it can be condensed down a little smaller. Sometimes like a research paper, the whole paper itself often takes the form of a CER over multiple pages, okay? Now, this matches pretty nicely with what science is in a nutshell. I kind of boiled down science into one sentence. This was something I wrote myself. I think this is maybe a little simplified, or in fact, I know it's a bit simplified, but it helps us for our argument. When we are doing science, what is a scientist doing? Fundamentally, they gather evidence to describe why the evidence supports how the universe works. It's those three things. They need evidence. They use that evidence to describe why the universe is acting in a way that they think, okay? Now, notice, while we often write a conclusion as C and then E and then R, science is not often done that way. In fact, it's rarely done that way. Usually, we look at the evidence that's been gathered, we use that evidence to make a claim, and we explain why that evidence is supporting that claim. So I just want to be a little clear. How we conclude maybe a scientific paper or a lab is not the same way that we conduct scientific experiments. We don't make a claim first. That's almost the antithesis of doing science. Usually first we are gathering evidence, we are then analyzing that evidence to make a conclusion. But when we write up a lab, when we say, hey, this is what we learned, we like to, because it's nice and and concise and it's easy to read, we start with the C, the claim, and then talk about the evidence and the reasoning. Likewise, maybe you're familiar with like the scientific method that you may have learned in like middle school or elementary school, or maybe in more recent science classes. But just know, while that's a good guideline, real science is messy. It doesn't follow this super simplified structure. It really depends on what the science or what the researchers are doing. Some start with observations and they use those observations to make theories and then models and then predictions. Sometimes a scientist is going to just ask a question, and then based on that question, maybe they make a computer model and then they put that into real world effects. So there's not really just one right or wrong way to do science, but how we summarize, how we conclude is often with this CER, okay? So that's the main idea. We often write it when we're finishing up our labs as claim, then evidence, then reasoning, but just realize that that's not how science is conducted. This is how we are summarizing, but we're not starting a scientific experiment with a claim. That's maybe a slippery slope because you want the evidence to inform whatever scientific conclusion you're going to end up with, okay? So we're just about done. If you're in my own class, I will have some resources for you. This is the same image on this next slide. Oops, I'm sorry. Right here. If you're in a different class or if you don't have me as a teacher, you could certainly find examples of how to write claims and evidences and reasoning. Some sentence starters are often helpful, okay? Now, also, if you're in my own class, we'll do some early work using like a graphic organizer. Again, the claim is usually pretty short. So in this own organizer that I made, it's a small little piece. Really what we focus on is the evidence and then the reasoning, because this is what is supporting our scientific argument, okay? Last thing I have for you, then our video is going to be all wrapped up. Let's look at an example, okay? I kind of made up just in my head a little model example that we could use to write a CER. This is overly simplified. Maybe it's a little obvious, like, well, of course this is true, but that's not what's important. What's important is seeing how we can write a claim, evidence, and reasoning as a way to finish, to finalize, to summarize, say, a lab experiment. This is what it says. When objects appear to move faster, they will travel a greater distance in a certain chunk of time. Okay? Releasing a marble, this is kind of summarizing the lab. Imagine I had a marble and I released it from this ramp, and then for 5 seconds we measured how far it traveled. Maybe we had like a smartphone which can do like slow motion video and we can see exactly how far it travels in a certain chunk of time. Anyway, we measured the distance, how far it traveled in 5 seconds in this setup, and then we repeated the setup so that the ramp is steeper. So it seems like the marble is going faster, and again, in 5 seconds we measure the distance, and in this example, let's pretend we measured a larger distance. Anyway, releasing a marble from a small incline, it traveled 2.7 feet when we timed it rolling on the floor for 5 seconds. That's what this is showing right here. Repeating for a steeper ramp, such that the marble seemed to go faster, it went 19.5 feet after those same 5 seconds. We measured a larger distance in the same amount of time for that marble moving with more speed, so it seems correct that fast things travel farther in the same chunk of time. In this little paragraph, this little summary, there is a claim, there is evidence, and there is reasoning. Can you pinpoint which is which? Maybe pause the video, but I'm going to go over the answer, okay? Here is color coordinated, the claim, evidence, and reasoning. The answer to the lab is the first thing I wrote down. We did this maybe silly lab, but what we figured out, well, when things seem to be going faster in red here, they travel a greater distance. They go farther in the same chunk of time. In blue, this is my evidence. Maybe earlier in the lab, we had a data table and we were writing down our values. But the evidence from our lab was we used maybe our smartphones and their high-speed video, and after 5 seconds, we measured how far they traveled, 2.7 feet. That was a measurement. 19.5 feet, that's a measurement. So that's our data, that's our evidence. Why is this evidence important? That's what I have in green. This is what students often forget to include. Why does this data support my claim? Well, it's obvious, all right? If I'm going 19.5 feet over here, and here I was only going 2.7 feet, well, when the marble seemed like it was going faster, it traveled a larger distance, which is exactly what my claim is saying. Okay, so that's how we summarize our experiments. We write our claim, we include the evidence that we took probably from a lab in a science class, and then we also tie that evidence back to our claim using a reasoning sentence or two. Okay, that's all I got. Thanks a lot for watching.